Look, stopping a car is something most of us do without a second thought. You see a red light, you press a pedal, and a complex system of pads, rotors, and friction does the dirty work for you. Your car's kinetic energy turns into heat, and you come to a nice controlled stop, right at the line. It's a simple, elegant solution for a few thousand pounds of metal on a solid road. But when you're talking about stopping something that weighs hundreds of thousands of tons floating in a liquid, well, the rulebook gets tossed right out the nearest porthole. There is no magic pedal, no friction to grab onto. It's a whole different kind of dirty job. The fundamental problem is the medium itself. Your car has the advantage of solid ground and grippy tires. A ship has water. Lots and lots of water. Trying to stop a massive vessel by creating friction in water is like trying to grab a fistful of smoke. Water is designed to let things slip through it, which is great for getting a ship moving, but a real headache when you need it to stop. The sheer momentum of a container ship, a vessel the size of a skyscraper laid on its side, is just staggering. You can't just fight that kind of force with a simple mechanism. You have to outsmart it. This is where the real work begins, the kind of work that doesn't involve a flashy button but a whole lot of planning and a deep understanding of physics. The folks on the bridge of these colossal ships aren't just steering, they are constantly thinking miles ahead. They have to, because a decision made right now will have consequences that unfold over the next hour. Unlike your daily commute, where a sudden stop is an option, for a ship, a sudden stop is a full-blown emergency maneuver that puts incredible stress on the vessel and its crew. It's a game of chess, not checkers, played on a board the size of an ocean. So, forget everything you know about hitting the brakes. We need to dive into a world where stopping is an art form, a carefully choreographed ballet of drag, thrust, and hydrodynamics. It's about manipulating the water, not fighting it. It involves using the ship's own design against its forward momentum, turning the very forces that help it glide into the forces that will bring it to a halt. It's a lesson in patience and power, where the biggest tool in the toolbox is foresight. And like most dirty jobs, it's a process that is absolutely fascinating once you pull back the curtain and see how it's really done. The most common way to stop a ship is also the least dramatic. It's called a controlled speed reduction, which is a fancy way of saying you plan way ahead. I'm not talking about looking a block down the road, I'm talking about seeing your destination, when it's still a tiny speck on the horizon, miles away. The ship's voyage plan, prepared long before it even gets close to port, has specific points marked on the chart where the process begins. This isn't a last-minute decision, it's a carefully plotted sequence of events that will unfold over a very long distance, sometimes over the course of an hour or more. It all starts with a simple command to the engine room: reduce the power. The engineer doesn't just cut the engine, they dial it back in small, deliberate steps. The ship might go from full sea speed down to full ahead, then to half ahead, and so on. The propeller keeps turning forward this whole time, which is a critical detail. By keeping that propeller spinning, even at a lower speed, it ensures a steady flow of water over the rudder. This means the captain and the pilot maintain full steering control, which is something you never want to give up unless you have absolutely no other choice. As the engine's power is reduced, a new force starts to win the battle: drag. You see, a ship moving through water is constantly fighting the drag of its own hull. When the engine is pumping out immense power, the thrust from the propeller easily overcomes this drag. But as you dial back that thrust, the drag starts to take over. The water pushing against the massive submerged part of the hull acts like a gentle, persistent brake. The ship's incredible momentum starts to bleed off, slowly but surely, as the drag becomes the dominant force. The vessel finds a new, slower equilibrium. This entire process is a perfect example of using the environment to do the work for you. Instead of fighting the ocean, you let the ocean's natural resistance do the heavy lifting. It's efficient, it's safe, and it keeps the crew in complete control of their vessel. But it requires an incredible amount of space and time. A supertanker moving at cruising speed might need 5 to 10 miles to come to a complete stop using this method. That's why you see these giants slowing down so far out at sea, beginning their long, graceful goodbye to speed long before they ever see the dock. So, what happens when planning fails? What if another vessel appears out of the fog, or an obstacle is spotted dead ahead with no time for that gentle miles-long slowdown? This is where sailors have to get creative and, frankly, a little dirty. One of the most effective tools for an emergency stop isn't the engine at all, it's the rudder. The goal is to create as much drag as humanly possible, as quickly as possible. One way to do this is with something called high-frequency rudder cycling. It sounds complicated, but the idea is simple. You turn the rudder hard to one side, then immediately hard to the other, over and over again. The helmsman isn't trying to actually turn the ship. In fact, they reverse the rudder's direction just before the ship has a chance to swing its bow. By kicking that huge plate of steel hard to port and then hard to starboard in rapid succession, they are essentially using the rudder as a massive underwater speed brake. Each time the rudder is angled against the flow of water, it creates enormous turbulence and drag, scrubbing off speed without significantly altering the ship's course. It's a violent, noisy maneuver, but it can dramatically shorten the distance it takes to stop a vessel in a straight line. If you have a bit more sea room and need to stop even faster, you can resort to a full-on emergency turn. By putting the rudder hard, over to one side, and holding it there, the ship is forced into a very tight circle. As the ship's bow swings around, the hull itself is no longer slicing cleanly through the water. Instead, the side of the ship becomes exposed to the direction of its own momentum, creating a massive wall of resistance. This generates an incredible amount of drag, far more than the rudder alone could ever produce. A ship can bleed off almost all its speed within just a few of its own lengths using this method. Of course, the downside is obvious. You end up pointing in a completely different direction, way off your original track. But if the alternative is a collision, a captain will gladly take the detour. These rudder maneuvers are a testament to the ingenuity of mariners. They show how a tool designed for steering can be repurposed in an emergency to do a completely different job. It's about knowing your vessel and understanding how to use every part of it to get out of a tight spot, even if it means turning the ship itself into its own brake. When all else fails and you need to stop now, there's one final, desperate option involving the engine, the crash stop. This is exactly what it sounds like. The bridge rings down an order for full astern, telling the engine room to throw the ship's massive propeller into reverse. This is the nautical equivalent of pulling the emergency brake on a train. The propeller, which was pushing tons of water backward to create forward thrust, now violently tries to claw at the water and push it forward, fighting against the ship's colossal forward momentum. It's a brutal, last-ditch effort to stop a moving mountain. However, a crash stop comes with some serious and dangerous trade-offs. The moment you put that propeller in reverse, you lose almost all steering control. The reverse wash of water, known as propeller walk, creates a chaotic flow around the rudder, rendering it practically useless. The ship will often slew sideways unpredictably. Furthermore, the propeller isn't designed to work efficiently in reverse while the ship is moving forward. It struggles in a partial vacuum and can cause severe vibrations throughout the vessel. It's a move of desperation, used only when a collision is imminent and unavoidable otherwise. Now, what about the most iconic piece of ship equipment, the anchor? Many people imagine that in an emergency, you just let that giant anchor go, and it digs into the seabed to stop the ship. This is a dangerous myth and something you absolutely never do on a ship moving at speed. An anchor and its chain are designed to hold a stationary vessel against wind and current, not to stop a moving one. Dropping an anchor while underway would be catastrophic. The immense force would likely snap the anchor chain or rip the windlass, the machine that holds it, right off the deck. It's a recipe for disaster. In the end, stopping a ship is a job that relies on brains over brawn. It's about foresight, planning, and a deep respect for the laws of physics. Whether it's the long, gentle slowdown from miles out, the clever use of the rudder to create drag, or the desperate gamble of a crash stop, every method is a trade-off between time, distance, and control. Anchors are for parking, not for braking, and unlike your car, there's no simple pedal to get you out of trouble. It's a dirty job that requires skill, patience, and a healthy dose of respect for the unforgiving power of the sea.